Hey everybody, I think I got my technical difficulties worked out. I'm ready to go over chapter 5.2 with you. 5.1, we already pretty much finished. I think there was a little bit left over, but I'm going to let you try to handle that. If you get stuck on it and you don't feel like you did very well, I'm going to let you come to me and let me know, Mr. Boyd, I would like to try again on some of those problems, but I think you'll be able to handle it. It's not that hard stuff. All right, so today we are going to be moving on. Look at that. How nice does that look? We're going to be moving on to chapter 5, section 2, and this is on rational functions. So we will be finding the domain of a rational function, finding the vertical asymptotes, and the horizontal or oblique asymptote of a rational function. You are going to be learning something today called Bobo Botten eats DC. Bobo Botten eats DC. That's the thing I want you to remember. It's going to help you find vertical asymptotes, horizontal asymptotes, oblique asymptotes, end behavior, things like that. All right. So first of all, what is a rational function? A rational function can be written in the form r of x equals p of x over q of x. It's just two polynomial functions that are being divided. What's important is that the denominator, the q function, cannot equal 0 because you know that you cannot divide by 0. So that q of x has to be something other than 0. Not only that, but the denominator cannot equal 0 at all. So if that denominator was something like 2x plus 1, what value of x would make that denominator equal to 0? You would take that denominator, 2x plus 1, set it equal to 0, and then solve. So if 2x equals negative 1, x equals negative 1/2. So if I have some kind of function up on top and the function on the bottom in the denominator is 2x plus 1, negative 1/2 would not be in the domain. Because if I put negative 1/2 into this function, if I evaluate it for negative 1/2, that's going to give me a denominator of 0, and that is not allowed. All right, so so the denominator cannot equal 0. Let's go ahead and take a look at an example. So in this function, r of x equals 2x squared minus 4 over x plus 5. Well, the numerator is my p of x, and the denominator is the q of x. So what value of x would make the denominator 0? Take x plus 5, set it equal to 0, and then solve for x. If you do that, you get x equals negative 5. That means that x can be any value. It's the domain of x is the set of all real numbers except negative 5, because negative 5 would make the denominator equal to 0, and that's not allowed to happen. So the domain, we would write it in set, in set notation. Where is my thing? There we go. The domain in set notation is all values of x. Remember, this line means such that x does not equal negative 5. So that's that one. How about this one? What values of x would make the denominator 0? Well, set x squared minus 4 equal to 0 and solve. I can subtract 4 from both sides, and I get x squared equals 4. And if x squared equals 4, I can take the square root of both sides. But don't forget, you got to do plus or minus when you take the square root. So x could equal positive or negative 2. That means, since I'm not allowed to have a 0 in the denominator, x is not allowed to be negative 2 or positive 2. So that's how you would write the domain. It's all values of x such that x does not equal negative 2 and x does not equal positive 2. How about this one? X squared plus 1. When would that equal 0? Well, subtract 1 from both sides. X squared equals negative 1. So what real number can you square to get negative 1? And we know that the answer to that is I. That's the only solution to the equation. X squared equals negative 1. It's just I. And remember, we're talking about real numbers. We're not using imaginary or complex numbers in this situation. And since I is not a real number, that means any value of x, any real value of x, would give me a denominator that's not equal to 0. So all real numbers are going to be in my domain. No number on a number line is ever going to make this denominator equal to 0, because anything you square will be 0 or positive. And when you add 1 to a 0 or a positive number, it's always going to be positive. So all real numbers. And then finally, right here, x minus 1. X minus 1 equals 0. So if I add 1 to both sides, x equals 1. That means the domain cannot include positive 1. Pretty easy to understand. So what about this function? What value of x would give me a 0 in the denominator? If x squared equals 0, I'll take the square root of both sides, positive or negative. The square root of x squared is x, and the square root of 0 is 0. But because 0 does not have a positive or a negative, x equals 0 is the only value that is not in the domain. So the domain is a set of all x values such that x does not equal 0. 0 is the only number for x that will make the denominator 0. That means since x cannot equal 0, there must be nothing happening when x equals 0 right here. And you can see that, in fact, there isn't anything. If I go straight up, there is a vertical asymptote. There is nowhere on this vertical line that this blue curve will ever, there's nowhere that this blue curve will ever touch the red vertical asymptote on either side. It will get infinitely close on both sides, but there will always be some space in between. It will never touch. Okay, what about this one? It says to graph this function. Well, I want you to see this and recognize it for what it is. This is just a transformation of a standard radical or rational function. So r of x equals the number 1 over x minus 2 squared. Well, isn't that just x squared, except I'm subtracting 2 from x? And if I add 1, isn't that just taking this and adding 1 at the end? So really, all I've got is a rational function that has been transformed. So what I'm going to do, if I can figure out this pen, there we go. So I'm going to have, oh, you know what? I need that red again. So x, and then this is minus 2 right here, and a plus 1 right there. The numerator is actually your a value, so a equals 1. But what was this number right here? Didn't that have something to do with whenever you add or subtract to x? Weren't we calling that h last time? And when you add or subtract something at the end outside of x, we called that k. Remember, with this number, you have to take the opposite. So the opposite of negative 2 is positive 2, and the opposite of positive 1, or actually, you don't take the opposite of the k value. It's just k. So k is 1. Just want to check in to make sure that my recording's going okay, and it is. So let's go back. All right, let's think about what these changes do. Well, a is 1, that does nothing. When the absolute value of a is more than 1, it's a vertical stretch, and when it's less than 1, it's a compression vertically. H and K, we remember that those do shifts. So H goes with X, so it's a horizontal shift. So H is going to be a horizontal shift. Which way? Well, it's positive 2. Positive is to the right. 2 units. K is the vertical shift. It affects Y. And since it's positive, up is the positive direction, so it's going to shift up 1 unit. All right, let's see if we were right. So here is the original function, y equals 1 over x squared. It looks like this. There's a point at 1, 1. There's a point at negative 1, negative 1. When we replace x with x minus 2, yep, it shifts to the right 2 units. So it moved to the right 2 units, and that's where my new vertical asymptote is. It was at 0, because 0 squared, if I put in a 0 there, 0 squared equals 0. But when I replace it with x minus 2, what number minus 2 gives you 0? Well, it's a positive 2. So that is where my vertical asymptote is now. It's at x equals positive 2. Finally, I've got a plus 1 at the end. I know that's going to shift my graph up by 1 unit. So notice that I've got a horizontal asymptote at the x-axis right here. When you shift this graph up by 1 unit, the horizontal asymptote shifts with it. And that's the line y equals 1 for the horizontal asymptote. And that's all that's happening there. 2 shifts, 1 to the right and 1 up. When you shift a graph in a particular direction, the asymptote travels with it. This is just analyzing tables to see what's happening with end behavior. Okay, so let R denote any function. So R of x is the function. If as x approaches negative infinity or infinity, that means if I've got some function and as I go to the left forever or as I go to the right forever along x, if the values of x approach some fixed number L, so let's call this L. Let's say my graph approaches L. It gets really, really close to L, but it never quite touches it. It gets infinitely close. Sorry about the curvy y asymptote there. And maybe it does the same thing on the other side. It never quite touches L, but it gets infinitely close. Then we say the line y equals L. That's this horizontal dotted line, y equals L. That horizontal dotted line is what we call the limit of the graph. It's the vertical limit. It never quite reaches it. And that L stands for the word limit. If as x approaches some number c, the values of the absolute value of the function, that is, as x approaches negative infinity or infinity, then x equals c is a vertical asymptote. So here's what that looks like. If as x approaches c from either direction, so let's say I've got a graph that looks like this. It gets infinitely close to c, but never quite touches it. And maybe it does something similar over on this side. Excuse me. If that happens, then you have a vertical asymptote. This is like the third day that I've been trying to get this working. I've spent like a couple of hours where I've where I've been making videos, not even realizing that the sound wasn't recording. So if you notice I've changed t-shirts and there's different lighting, that's why. I'm going to get back into it because I'm pretty sure the audio is working now. All right, so when we're talking about end behavior of a function, as x approaches infinity, that's what we're talking about. This expression right here talks about how to discuss the limit of a function. So we write it this way. We say the limit as x approaches some value of that function, which we're calling the function r of x, equals some ending value, and this is the y value that it approaches. Well, let's follow this function to the right. As x approaches positive infinity, as I go to the right forever, what is happening to the y values? They're getting infinitely close to this y value, which we're calling L. So we say that the limit of this function as x approaches infinity, the limit is just L. Now, I can't really see what's happening as x approaches negative infinity on the left. But sometimes you'll try to discuss the end behavior in the other direction. You say the limit as x approaches negative infinity of the function r of x. Maybe it also approaches L. Maybe it gets infinitely close to that imaginary horizontal line, in which case it would have the same limit either way. Sometimes that happens. That's what they're talking about in letter B. It would be the limit as x approaches negative infinity. Now, sometimes we don't want to talk about the limit as x approaches infinity or negative infinity. We want to talk about as x approaches some value c. So this x value is c, and the function is going to approach it. As the x values get closer and closer to c, what's happening to the y values? Well, I've highlighted the right side, and that's called the positive side. So c plus or c positive. Let me rewrite that. So, and we call it the positive side because it's on the right, and the right side is the positive side of the graph. Well, the y values are going up forever to infinity. So we say the limit of that function r of x as x approaches c from the right side, c plus, is infinity. What about the left side? What is the limit as x approaches c from the left side, the negative side? Well, we can see that it's also approaching infinity. And what we can do there, since the limit is the same on both sides of c, instead of splitting it into two different parts, c plus and c negative, because the limits are both the same, they're both infinity, we can just combine that into one statement. We can just say the limit of r of x as x approaches c from either side is the same value. It's infinity. So that's an important thing to know. Finally, sometimes at a certain value c, the limit on the right side and the limit, see, technical difficulties. The limit on the right side and the limit on the left side might be different. So the limit of r of x as x approaches c from the positive side here is positive infinity, but down here the limit of r of x as x approaches c from the negative side is going down to negative infinity. So what would the limit as x approaches c be? Not c plus or c minus, just c. Well, that would not exist. So we write DNE, or you can write does not exist. Either way, for a limit to exist, the limit on either side of that x value has to be the same. Has to approach the same value, either both to infinity or both to negative infinity, or maybe they both approach the same finite y value. But anyway, that's a little bit about about horizontal asymptotes and vertical asymptotes. So right here, we're talking about a horizontal asymptote. And that would have a limit equals L. Sometimes L is a number other than 0, and sometimes it's 0. And I'm going to teach you a tool called Bobo Botten Eats DC. I mentioned that earlier, but it's going to help you figure out what the end behavior is of a function. And then sometimes, this is not end behavior, sometimes we have a vertical asymptote. With a vertical asymptote, we approach an x value and the y values go to infinity. With a horizontal asymptote, the x values approach infinity and the y values approach some y value. There's also a third type of asymptote. It's an oblique asymptote. And this happens when the function has a degree on top and a degree on bottom that is one less than the degree on top. So for example, if I say r of x equals x to the fifth over 3x to the fourth minus 2. Notice that the degree on top is 5 and the degree on bottom is 4. 5 is 1 more than 4. That means that this graph, if I put it into a graphing program like Desmos or whatever, graphing calculator program is what I was trying to say, it would show that there is a diagonal line that this curve will approach on one side and actually on the other usually. So find the vertical asymptotes of a rational function. I'm actually going to do you one better. I'm going to show you how to do this. You're going to love this. Okay, I'm going to take this expression, and I'm actually going to copy this expression into a new slide, and I'm going to show you Bobo Botten eats DC. Or not Bobo Botten eats DC. I'm going to teach you how to factor an expression or a function. Let's just show you what I'm going to do here. Okay, so here's what we're going to do. We're going to figured out my problem. I had a hotkey set up on this that is also a hotkey on the recording software I'm using. The hotkey on this thing is supposed to, when I hit it, hide all the annotations that I've made. But that hotkey, that hotkey is also muting my mic, so I'm accidentally hitting it sometimes and muting the microphone in the recording software. That's a huge relief, so now I know I won't be screwing up any more videos and I can get these out to you on time. All right, so here's what we're going to do. We're going to take this expression and we're going to factor it. So the numerator, I see that it's a difference of two squares. So if you remember this, a squared minus b squared. If you have something like that, you can factor it by taking the square root of a and the square root of b. Square root of a, or the square root of a squared is a, put that here and here. The square root of b squared is b, that goes here and here. And then because it's the difference of two squares, I can do one of them plus and one of them minus. If you're not sure if that's actually correct, you can FOIL it. You do a times a is a squared, b times negative b is negative b squared, and then the other two terms are negative ab, and this here would be positive ab. Well, negative ab and positive ab add up to 0, and that gives you just a squared minus b squared. So if you have something that's the difference of two squares, then you can very easily factor that by just taking the square root of each side. So x squared, the square root is x, so x and x. 9, the square root is 3, so I put a 3 and a 3. And since I have the difference of two squares, one of them is plus and one of them is minus. The denominator, I'm going to factor this quadratic expression by remembering that I take a and c. Well, a is 1, c is negative 21. So a times c is negative 21. What two numbers can you multiply to get negative 21? But when you add those same two numbers, you get b, which is positive 4. b is positive 4. Turns out the numbers are 7 and negative 3. 7 plus negative 3 is positive 4. So my factors are x plus 7 and x minus 3. Well, that brings up something kind of neat right here. Look at these two terms. X minus 3 is being divided by x minus 3. They cancel each other out. If you have a situation like that where two terms in a rational function cancel out because they're the same factor on top and bottom, then you have what's called a hole, or a removable discontinuity. Removable discontinuity. So what you do is you take that factor, x minus 3, set it equal to 0, and then you solve. So if I add 3 to both sides, I get x equals 3. So that is where there will be a hole in this graph. I'll give you an example here, just a second. All right, so I've got this expression right here, this function f of x equals x minus 2 times x minus 1 all over x minus 2. Notice what shape it makes. It makes a straight line. Now if I were to make a table of values here, so I'm going to call these just x, and I'll call this f of x. Oh, no capitals, sorry. F of x. And I'll just choose a few values here. So let's say -1, 0, 1, 2, 3, 4, 5. So there's this table. When x is -1, y is -2. I can see that right here. When x is 0, y is -1. I see that right here. All 6 of these points are here. But notice the point that's missing. The point that's missing is 2, when x is 2. If I zoom in to that point, you won't see anything weird going on. And that's because computers and calculators have a hard time doing this. But what's going on is that there is an invisible hole there. There is not actually a point. I could zoom into that point to infinity. I could get infinitely close to the point x equals 2, y equals 1, or yeah, I guess 1. And there would never be anything appear there. Even though it looks like there's a point that exists, there's actually an open circle. So there's actually an open circle. And it would look something like this. What was the equation? X minus 2, x minus 1. So if I say f of x equals x minus 2, x minus 1 over x minus 2, what's happening is these x minus 2's are canceling out, and all that's left is that function, f of x equals x minus 1. Well, you recognize that, I'm sure, as a linear function. It is a graph that has a y-intercept at 1, and it has a, or -1, and it has a slope of 1. So it's going to look like this. That's the line. The problem is, though, that at 2, there is no point there, because when I put a 2 into this original function, I get 2 minus 2 times 2 minus 1 over 2 minus 2. And what's the value of that? Well, 2 minus 2 is 0, 2 minus 1 is 1, and 1 times 0 is 0, over 2 minus 2 is 0. 0 over 0 is undefined. In fact, we have a special name for 0 over 0. It's called indeterminate form. You get into that when you start to take calculus. You'll learn about L'Hopital's theorem. So it's a whole thing. So what we end up doing at this point is you make the line, except at 2 you put an open circle. The calculator and the computer